Small miracle, I remember to record. Unusually small number of people.
Hello, Professor.
Hi.
In fact, today is their holiday for Chinese.
Oh,
So
no wonder.
maybe the students are too free to join in our class. Yeah. Yeah, but I think you can start now. You can start now. Yeah.
I guess it's recorded, so that helps. Okay, I'll start now. So we're going to switch gears a little bit and talk kind of about, well, deep learning, but as related to neuroscience. So so far, up until now, so what was our approach? So choose connection strengths. You know, it's a holiday in UK too. WIJ. We also chose a model for neurons. And we chose a really simple linear integrated fire. Okay, so we chose our model and then we computed or determined and mainly analytically. You notice I didn't really do any simulations. We didn't need any simulations because the math would kind of easy the behavior of the network. So it's always nice to do things analytically, but it was a bit limited, right? We understood, and so what did we do? We basically, so the cases we considered were randomly connected networks, and then point attractors, also known as Hopfield networks, and line attractors. So a very limited class of computations. The brain, on the other hand, does really complicated things. I mean, this approach of choosing a connection strength and choosing the model is not, as far as we can know, explain complex behavior like sitting and listening to this lecture. And so to understand complex behavior, well, let's just say to model, let alone understand, model complex behavior. So we need to think about learning. Learning, and particularly about learning the weights. Okay. So, and And so this is really what the next couple of lectures is going to be about. Actually, the next 4 lectures. I switch the order. I'm going to do deep learning now, and then synaptic plasticity, actual learning in the brain. And so learning is critical to all this. And I think it's really the most important part of neuroscience. So I'm going to start with a little bit of background first, and then I'll give you an outline of the next couple lectures. So here's the picture that I kind of have in my brain about the brain. So here's your brain. And the input to your brain, input is basically, it's sensory. So vision, actually input, so images, sounds, smells, I guess all the senses we have. I'm just going to call this S. I think I should call it, it's kind of important. So I'm going to call this S of T. As you think of this as a high dimensional vector. Okay, so the images are very high dimensional. I mean, you have about 10 million photoreceptors, 1 million retinal ganglion cells. You have lots and lots of input coming into your brain at any one time. And the output is movement. Okay, so the output is, we'll call this M of T. And M of T is about, you have about 600 muscles. So this is about 600 dimensional. Okay. The other output is internal things. You regulate your heart rate, your digestion, things like that. But we kind of won't worry about this. And maybe to complete model of the brain, we care about that. But we're gonna sort of ignore this. Okay, we're gonna focus on movement. So we can think of what your brain does. Is your brain just mapping? It's a mapping from M of T, about a 600 dimensional vector, equals some function of S, and I write this 0 to T. So this is birth. And one of the things that makes the brain hard to understand is really past sensory input has a big effect on your current action. So you can think of sort of the recent past, reading a book. So basically the beginning of the book, so beginning affects how you react to the end. So, you know, this is true of novels. You can read the last page of a novel, it won't make much sense unless you read the rest of it. It's really true of textbooks, right? If you pick up a textbook and you try to read the last chapter, it probably won't make sense. The other thing, I mean, just understanding this lecture, or hopefully you understand this lecture, that depends on lots of past information, lots of past knowledge. Okay. So you have to know English. You have to know a certain amount of math and technical things about the brain. There's tons and tons of stuff you need to know. And that came from sensory input that you might have gotten decades ago, okay? So this is a really, really complicated mapping. And so sort of historically, this is mainly in the 60s, so the goal of AI, artificial intelligence, was to recreate this function on computers. Okay. And I was reading a book on AI, and at the time, people thought this would be easy. Researchers, let's say researchers. So researchers in the field thought this would be easy and the reason they thought it would be easy is because people are stupid. I'm not making this up. So that was the original. This was in the 60s. This was like 1960s. I mean, if you think, and people really typically aren't that bright, but this did not work. So people maybe, so didn't work. So it didn't work is an understatement. So AI crashed and burned. And the reason is people may be stupid, but people are flexible. And they try to use symbolic logic. They could never capture the flexibility that we see in real people, okay? And so AI actually disappeared for a long time. They changed, the reason there's a field called machine learning is because AI, artificial intelligence, had such a bad reputation, they needed a new name, although it's coming back. But here's the current view. I'm gonna actually, so remember our picture, this is pictures sort of important. So we have the brain. So we have the brain. So input is of t, output is m of t. So here's the current view has shifted somewhat, at least from the point of view of AI. Instead of thinking, so m of t, so let's start the old view, remember? So the old view, m of t equals some function of s 0 to t. So the new view is that m of t is a function of some parameters, which we'll call weights. In the case of the brain, it's synaptic weights, and s of t. So this is sort of, t is now the current time. So this is within the last few seconds. Okay. So, the muscles you move, the output of your brain, you just need to know the input the last couple of seconds, and all this past information is stored in the weights. Okay. And then the weights are updated. Coming to some rule that dw dt, you think about this, equals some other function which depends on both the weights, also s of t. So there's a learning rule. Okay. So this is updated version of This is the updated version of AI. And basically, researchers gave up on trying to understand this transformation from input to output. Instead say, it's too complicated, we're going to learn it. Okay. And it's really, this is a deep learning revolution, and it has worked in many ways amazingly well. And hopefully we'll learn a little bit about why. Okay. And so if you're sort of if you're and then we want to contrast. So there's sort of two things. If you're a deep learner, so you care about any set of equations So when I say equations, I'm really referring to these functions. These set of equations that generates brain-like behavior. And we're going to talk a little bit about that, what that means. If you're a neuroscientist, you care about the equations the brain uses. Okay. And so the reason neuroscientists are interested in deep learning is because the equations that sort of any set of equations you find are probably going to look a fair amount about like the equations the brain uses. Okay. So what we're going to do for this next couple lectures, we're going to talk about deep learning, basically making up the kind of equations that deep learners make up. And you might ask, so the natural question is, does deep learning have anything to do with neuroscience? Okay, and it's a good question. And neuroscientists actually debate this question. I think the answer is yes, for the following reason. Okay. So here's something that's almost philosophy, but not quite. So neuroscience is trying to understand how the brain works. So this is our goal. Understand how the brain works. Brain works, okay? So I'm not sure, people rarely say what understand means. And I actually thought about this for a long time before I realized that in science, understanding is well defined. So in science, so understand really is about bridging two levels. And in neuroscience, understand, well, let's say neuroscience in particular. In neuroscience, understand equals link. So neural equations to behavior. And the neural equations are just this one. So motor activity is some function of the weights in the activity. activity in your brain. This is really just given by a bunch of neurons. These could be linear integrated fire neurons or something more complicated, coupled via synaptic weights. So those are the sort of the output. And then there's a learning rule that goes on. So when we say in neuroscience, we want to link neural equations, the neural equations we're talking about are, linear integrated fire neurons and some learning rules. Oops. Behavior, okay? So the neural equation we're talking about is the ones we've been writing down, except we haven't written down learning rules. So that's what understand means. And the link, we want to talk about how one makes a link, but the problem with this is that right now, we don't know the equations. And for a simple reason, we don't know the weights. Okay. And there are a lot of weights, right? So in humans, there are 10 to the 14 weights. There are 100 trillion weights. So we're missing a lot of parameters. Even in the fly, there are a billion weights. And by the way, we might get the flies from the connectome, okay? But certainly humans, there's no chance of measuring these weights, okay? There are just way too many weights to measure. And so deep networks, the utility of deep networks is go to a new page. So, deep networks can a candidate set of weights. Okay. So this actually has been sort of a small industry. It's a really common thing to do in the brain is to so this is, people do this for vision all the time. So possibly the most common in vision. Better handwriting. Most common in vision. So people train a deep network on object recognition. And compared to what you see in the brain, compared to neurons in the brain. And agreement is okay. It's not great. And I'm not really sure. I think it's not good enough that we can say we understand vision, but it's getting, okay. So the idea is by learning something about deep networks, and if we understand deep networks enough, maybe we can make them do more powerful things and get some insight into the computations the brain is doing. Okay. So that's the reason, the rationale for studying deep networks is maybe because they look like networks in the brain. The equations are similar, and there's a chance they'll tell us something about the brain. Okay. So and really in some sense, at least for supervised learning, everything's the same. Okay. So that's background. Let me now give you an outline of what I'm going to talk about today. So I can start off with sort of a sort of, I don't know. So the intro, deep learning. It's got a lot of hype today, but it's really just nonlinear regression. Okay. So honestly, if you understand linear regression, you understand deep networks. There's nothing really fancy about them. Two is they typically have lots of parameters. So remember, if you do linear regression in 1D, you're fitting a line through a cloud of points, and line really has two parameters: a slope and intercept. Actually, it's a day. So deep networks have lots of parameters. How do they work? So the conventional wisdom is if you have too many parameters, you overfit. Why do they work? Actually, I say why don't they overfit? And remember, the brain has 10 to the 14th, 100 trillion parameters. You just don't get 100 trillion training examples. It has to fit, it's got a lot of parameters and really not much data, okay? So that's gonna be sort of a little theoretical background. I'm gonna talk about backprop. Sort of the algorithm that everybody uses, including BAP. Let's talk about backprop, okay? And that's technical. This is math. This is math, and something you should all know. It's the backprop algorithm is super simple, but it's technical. And then we're not really, but it's important because we kind of need to know something about it, understand the rest. Then we have to consider wide networks. And mainly because things greatly simplify. Things greatly simplify. Okay. In wide network, things are a lot different. And finally, I'm going to talk about, so this is all so this is all, everything up here is supervised learning. Supervised learning means you're given a teaching signal, which doesn't really happen in the brain. So unsupervised learning is really most relevant for the brain. Okay, most of the information you get is unsupervised. You rarely get a supervised signal. You rarely get someone telling you what's right or wrong, except for your parents, and they don't even do that very often. And in some sense, everything is technically unsupervised. Okay, that's the outline. Okay, so let's start with sort of what's going on in the supervised learning setting. So supervised learning is really conceptually very simple. So we always have training examples. So we're going to call this x mu. So x mu, x is typically a vector. So y can also be a vector too, but we'll think of it as a scalar. Okay, so example, put this over here. Example. So X mu equals image and Y mu equals a label. So somebody gives you lots and lots of images, say this has a cat, this has a dog, this has an airplane, and so on. And what you want to do is train your network to produce as output a label, okay? Or else you might want to put in, you know, input is, stuff we're going to do is more relevant for this. Input is so X mu equals also, let's say, an image, and Y mu equals where you want to move your arm. And in this case, Y mu has to be a vector. But it's a low D vector, might be a vector. Say a vector in 3D. Okay, so you notice for both examples, so typically X mu is high dimensional. And Y mu is low dimensional. Dimensional, often, like we said, 1D or even categorical. Okay, so that's a setup. And then, so training examples, and then in some sense, we have an architecture. I'll give you examples. And so architecture is just a, think architecture, think of a function. So F, it's got to involve some weights and X. So architecture is really Y equals F of W dot X, X. So example, linear regression is linear regression. Y equals W dot X. Okay, just an example. And the reason, and for, you know, linear regression is actually still used for a lot of things, but for doing something like mapping, you know, image to a label, linear regression is not going to work. Okay, the decision boundary, say, between cats and dogs is just not linear. So instead we use deep networks. I'm going to write this down explicitly in a second. And then there's a loss. Which is L. I'm going to use squared loss, but it doesn't really matter. Squared loss doesn't use for cat. It can't be used for labels, but it can be used for where you want to move your arm. So it's 1/2 the sum on mu equals 1 to P of Y mu minus Y mu star of X. Okay, squared. So the squared loss, we can write 1/2 the sum on mu equals 1 to P of F of W comma X mu minus Y mu star of X mu squared. Okay, so we're trying to find the weights. So loss depends on the weights. L of W. And then the goal is to find the weights that minimize the loss. And really you want to minimize the loss on test data. And that's important because these deep networks often have lots of parameters and they're kind of easy to overfit. Okay, so that's a setup. And what we're going to do is we're just going to take a derivative, right? We can just we follow the gradient, we minimize the loss. In fact, let me so how do we do that? We minimize the gradient. So delta W, change in weight, delta W is equal to minus eta partial of L with respect to W. That's the learning rate. So we're going to go into this in more detail. Okay. So we just take a gradient, and we'll see in a second why that works. Okay. So before I talk about sort of the details of that, I want to give you a little understanding. So here's a crazy thing about deep networks. So deep networks often contain, in these days, they can contain billions of parameters. So deep networks contain more parameters than training examples. Okay. So this seems like a horribly bad idea. It seems like it can fit anything, right? And a lot of our intuition actually comes from low D. So suppose you have, you're trying to do a regression model. This is X and this is Y. And you have Y equals AX plus B. Okay, you're trying to fit this model. So fit a model, and you have one training example. X mu, Y mu. Okay, so this is our training example. Okay, and we have to fit a line through there. Well, of course, this is useless, right? We could fit this line, this line, this line, all these. So all these lines fit the data perfectly. Okay. It doesn't work, right? We wouldn't even think about doing this. If you tried to do this in the paper, you get yelled at. And yet we do this all the time. Typically there are, so images, you might have tens of thousands of images and 1 million parameters in these models. Okay, so why do they work? So it turns out that a lot of our intuition in low dimensions just doesn't apply to high dimensions. So I'm going to tell you something that is a little mind-boggling the first time you hear it, and honestly, I understand it, but only technically. I don't really have it. Well, I kind of understand. So we're going to try to fit a model. So this again, X and Y. So so let's say we have 5 points. 1, 2, 3, 4, 5. So we have five training examples. Okay. So what do they tell you never to do? Never fit a 5th degree polynomial. Okay. So because if you fit a 5th degree polynomial, problem is it's mainly these points are going to mess you up. You can get a curve that goes like this, like that, goes way down and goes up. Okay. So this is the 5th degree polynomial. Okay, this is a horribly bad idea. Oops. Okay, it's not going to make any sense at all, right? You go through every data point and it just doesn't generalize, right? The true data, I'll draw in a second, probably lives around over here. So instead, it seem to make a lot more sense, given the data is to fit, well, let's say a good idea, quadratic. Fit a quadratic function. Okay, fit something like this. Okay, I mean, may or may not be a good fit for the data, but at least it's not a horribly bad fit. Okay, so, but here's the thing that people realize. Actually, it's been known for a long time, but it kind of recently made its way back into people's minds. Is you can fit a 10,000 degree polynomial can't write polynomial. And what do you think happens? It's massively overparameterized. You basically go through every point. Okay. It fits the data reasonably well. Now, there's some technical issues about that. You have to start in a reasonable spot. Fits data reasonably well, you know, where the data is. Okay. In fact, it fits it almost as well as your quadratic. Let's say the quadratic was the right model, right? It's going to have about the same error on. So let's put the rest of the data in. Let's say the real data lives around. Oops. The real data lives around here. This is the real data. So actual data. So the actual data was fit pretty well by quadratic, but it's also fit, at least in this region. In here, our 10,000 degree polynomial actually fits really well. Now, of course, it's a high dimensional polynomial. As soon as you go away from the data, it's going to be a nightmare, right? It's going to go all over the place. So it's not going to fit well at all where the data isn't. But where the data is, it's going to fit fine. And this actually, I think this is probably what deep networks are doing. So overparameterization is actually only bad if you have sort of precisely the wrong number of parameters. Too few parameters is okay if you have a good model. If you have a bad model, if you're fitting this to a straight line, it might be a really bad model. If you have the good model, too small number of parameters is ideal. A medium number of parameters is horribly bad, but a large number of parameters is ideal again. Okay. And I'm going to actually do one more thing. Ask, okay, so how many training, so for a given model, how many training examples do we need? So I'm going to actually look at linear regression, sort of the one thing we understand. Take a brief prelude to do linear regression. Y equals w dot x equals the sum I equals 1 to n of w I x I. So the data is n dimensional. Okay. And we'll assume that we have P training examples. With P less than N. So we have more parameters than we have training examples, and we're going to run with gradient descents. So delta W, the change in weight, is equal to minus eta, the partial with respect to W of the loss, which is 1/2 sum on mu of y mu, which is W dot X minus y mu star squared. Okay. And if you take a derivative, this is equal to minus eta, the sum on mu of W minus X mu, minus y mu star, which is just a number, times X mu. Okay. So this is kind of interesting because basically this is just a scalar coefficient. It's just a scalar, right? So the weights only move in the direction of the x's. So the final weight, W, after running this to convergence, and it's always going to converge because it's convex, and we have, so W of t, or t equals infinity, after running this forever, is equal to W0 at t equals 0, plus the sum on mu of A mu X mu. Okay. And so this lives in a equals 1 to P, in a P-dimensional space. Okay. Okay. And remember, but W is n-dimensional. Okay. So if our data is n-dimensional, if our data really lies in the full n-dimensional space, so this won't work. If data lies in n dimensions. Right, I mean, you can imagine sort of, in some sense, this goes back to, well, and the reason is we've only, in some sense, I'm not sure how to draw this. It's kind of hard to draw because everything's high dimensional, but the true weight vector, let's say this is W star, this is ND, and we've pinned down a p-dimensional component of it. So we know W star in a p-dimensional space. Okay. So, and what that means is, so we don't know this. Okay, we don't know this component of the weight space, but if the data only lives in here, it doesn't matter, right? So this will work if data, if sort of the effective dimension, if D effective equals dimension of data is less than M, less than P. So this kind of intuitive, right? If your data, let's say you're doing regression in a really high dimensional space, right? Really high dimensional, but your data all lies, so your data all lives here, right? Then the fact that high dimensional doesn't really matter. You're really doing linear regression just along this line. You have to know where along the line of data lives. And as soon as you get 2 or 3 points, you automatically know. Okay. You can sort of be, well, you don't know for sure, but you see a lot of data points, you realize they all live on a line. You have to find, the direction along that line. Okay. So this is important. So conclusions, and then I'm going to take a break. So overparameterization is not bad, a bad thing. If you're very overparameterized. Overparameterized. So this is not obvious. It's just sort of a math fact. And the other thing that kind of makes sense, you can fit the data, sort of, let's say, find the right parameters. If P is greater than the effective. And this is number of training examples, remember. And this is dimensionality of data. Okay. And the reason deep networks must work on images is because images are fundamentally low dimensional. Right? There's really are some small number of features that tells you what's important, and you just have to find them. Okay, so we've been going pretty long. Let's take a break. And for 5 minutes, I'll save these to photos before I forget. I'll be around if you want to ask any questions. And then in 5 minutes, we come back and we will talk about some more sort of technical details. Okay, so let's go, let's start up again. Stop share. I hope I saved. Share contents. I did save. I should always double check. Good. Okay. So I want to do a couple of things. I've been talking about gradient descent, and I want to make sure that we know why gradient descent works. So we have some loss. So L, which is a function of weights, equals loss. And our update rule is delta W equals minus eta partial of L with respect to W. Okay. I'm going to use gradient descent. Everything I say applies to stochastic gradient descent, but it's a little more complicated to show. But what under this law, so we're going to assume eta is small, and I'll tell you what I mean by small in a second. So if eta is small, L, what happens to the loss under this? So L of W plus delta W equals L of W plus delta W dot partial of L with respect to W plus 1/2 delta W dot partial squared L respect to W dot delta W, just a higher order term in Taylor expansion. And so small, what we mean by small, small means small enough to ignore higher order terms. Order terms, okay? And that's non-trivial for high-dimensional Taylor expansions, but certainly you can, in principle, because delta W is proportional to eta, oops. Delta W is proportional to eta. If you make eta small enough, these things are small enough, because these terms are proportional to eta squared. The next one's proportional to eta cubed, and so on. Okay, so just make eta really small, and those terms will go away. Okay, so so this thing now is at least approximately equal to L of W, and for delta W, we'll just plug in this term. So it's minus eta partial of L respect to W dot partial of L respect to W. Okay. And this thing, of course, is non-negative. It's a dot product. Okay. So if the learning rate is small enough, the loss is always going to get either smaller or stay the same. And really the only thing that goes wrong is you may have a non-convex loss surface. So loss surfaces tend to be non-convex. Tends to be non-convex. Okay, so you might, if you're unlucky, you'll start here and you go down here and end up in sort of, this is, so this is loss. This is loss on this axis, and let's say X ID. So if you start in the wrong place, so starting in the wrong place, can be bad. Okay. So in the sense that the optimal place to be writes right here and you end up right here. So it's not that the deep networks have a structure it's not really known. So deep networks are highly convex, but it doesn't seem to matter. And people don't really know why. There's speculation, but it's not clear. Okay, so just to be crystal clear, I'm going to repeat this calculation with indices instead. So delta Wij in terms of indices, so that was in terms of vectors. I wrote delta W as a vector, it's actually a matrix. So delta Wij is really, I'm going to repeat this thing, is minus eta partial of L respect to Wij. Okay, and L of W plus delta W is approximately equal to L of W plus the sum on Ij, delta Wij, partial of L respect to Wij. And now we'll just take and put this in here. And so this thing is now equal to L of W minus eta, the sum on Ij, partial of L respect to Wij squared. And this, of course, now is this quantity here is greater than or equal to 0. Okay, so this gradient descent finds a local minimum. Local minimum. And the current view, so the current view changes with time, but the current view is basically the loss for a deep network looks like this. Lots of local minimum. But all equally good. And remember, this is a current view. Sometimes the current view is there are no local minimum, only one global minimum, but I think this one is probably correct. Okay, so I haven't really told you what a deep network is. So I'm going to actually define it now. You've probably seen this picture many times. X is the input, it's a vector. And then it's very simple. Not sure how I'd write this, and the output is Y. And these are all weights. And so between these, we have weights and a nonlinearity. Okay, weights. And then a nonlinearity. Okay. And the update rule is, so xi, neuron I in layer L. So I'm going to call this layer L. And the weights going into it are either the weights in layer L equals, so xi in layer L is some nonlinearity, sum on J of Wijl xjl minus 1. Okay. And then, of course, Y, if this is layer L, equals the sum on, usually it's linear, it can be nonlinear, but we'll keep it linear. Doesn't really matter. Sum on J of Wij L plus 1 xj in layer L. So the output is a linear combination of the inputs. By the time you get to the output, you're doing linear regression. But in between, we have a nonlinearity. And typical, it's a really simple one. They don't always use this. Typically, these days it's a ReLU. Oops. ReLU. Rectified linear unit, ReLU. So ReLU of X. Of X, this is 0, and it just looks like this. 0 here, and then 1 here, X here. So it's minimum 0x, simplest nonlinearity in the world. Okay. So this is a deep network. So this is a network. This is a setup. How do we take a derivative? Okay. So if we want to know how, in some sense, we want to know, if we change a weight, oops. So if we change one of these weights over here, right? We change one of the weights in the beginning. How does that affect the loss? It goes through all these complicated nonlinearities, okay? And finding that it's not obvious we can even take a derivative. But this is where backprop comes in. Okay, so I'm gonna rewrite our update rule, which is xi in layer L equals phi of the sum on J of Wijl xjl minus 1. We're going to call this, give this a name, and call this HIL. Okay, H stands for synaptic drive. So we want to know the partial of L, change in the loss, with respect to Wij in layer L. Okay, the first observation is we can write this as, so Wijl is a function of HIL. We can write this as partial of L, oops. Partial of L with respect to HIL times partial of HIL with respect to Wijl. And this is equal to partial of L with respect to HIL. And this quantity here is just, oops. So this is just xjl minus 1, okay? Take a derivative of this quantity here with respect to W, you just get out the x. So this is the thing, this is basically the backprop signal. Error signal. Okay. And we still have to find it, but that we can actually do. So what we're going to do is we're going to express this quantity LDHIL with respect to the backprop error signal in the next layer. Okay. So we'll write partial of L, just using, this is a chain rule with respect to HIL equals the sum on J of partial of L with respect to HIL L plus 1 in the next layer. Oops. HJ, that's actually a better handwriting. With respect to HJL plus 1, partial of HJL plus 1 with respect to HIL. Okay, and what we have, I mean, if you look at the network, right? So if what we're doing really is saying, how much, if we change, so HIL has a nice interpretation. HIL is really the drive to some neuron. It's the input to the nonlinearity. And what we're asking is, if we go back here, if we change the input nonlinearity here, that's going to affect the error. But we're going to express that in terms of what happens if we change the nonlinearity here. Okay. And if you know your outgoing weights, that's perfectly fine. We'll see that in just a second. Okay, so we can now just write down HJ L plus 1 equals, it's just this quantity, but with an L plus 1 instead of an L. Equals the sum, running out of indices, sum on n of W, I, N, L plus 1 to M, X, J, sorry, XM, XML. Okay, we just basically copied this. We changed a J to an M and L to an L plus 1. And now this is equal to the sum on M of WIM L plus 1. So XML is just phi of HML. Again, and that's given here, right? XIL, we just change I to M. Okay, simple enough. And what that means is that partial of HJL plus 1 with respect to HIL is this derivative, right? It's WIM. Shoot, sorry, gang. This I should be a J. It's WJM L plus 1. And we can look over here, and it's just derivative, phi prime of H. Sorry, the M has to be an I. HLI. Okay, so this derivative, I'm going to take this derivative here and put it in here. Okay, so this is equal to the sum on J of partial of L with respect to H JL plus 1. Shoot. With respect to H JL plus 1 times W JI L plus 1 times phi prime of HIL. Okay. So that's the backprop error signal. So we're going to actually, we have enough room over here. We're going to find delta IL is defined to equal partial of L with respect to HIL. So our update rule is delta IL is equal to, it's actually usually written like this, phi prime of HIL WIJ L plus 1 transpose of the matrix times delta JL plus 1. Okay. So if you know the error in layer L plus 1, and you know the weights from I to L, from I to the next layer, you know the error in the previous layer. Okay. So what we can do is, this is why it's called backprop. We start with the error of this layer, which is really easy to compute because we know Y star. Then we backprop, 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 backprop. And it kind of makes sense. If you look at this, so these weights are, maybe it's easy to see here, when you're backpropping this error signal here, you're using the weights in the next layer. Okay, this is layer L. These are the weights from layer L to layer L plus 1. And given that, it now makes total sense, right? If you're a neuron sitting here, you don't know how you're going to affect the output. You do know, if you know your output weights, how you're going to affect the next layer. Okay. But you have to know your output weights. Now, it turns out that, so let's actually write that down. So let's sort of summarize. So to compute weight updates, so you need partial of L respect to W, I, J, L. And that we saw was partial of L with respect to H, I, L times X, J, L minus 1. I think that's double check that that's right. Yeah. Okay. So this is the thing we care about. So, and then the other, so if you know partial of L with respect to H, with respect to H, J, L plus 1, and you know your outgoing weights, you can compute partial of, you can compute partial L with respect to H. Okay. So this part, you know your outgoing weights, is problematic. So neurons do not know their outgoing weights. Okay, 500 million years of evolution, and neurons don't know what their outgoing weights are. It seems kind of crazy, but that's the way it is. So classical backprop cannot be used in the brain. So rules out in the brain. There are actually now lots and lots of alternatives that work pretty well. People are trying to get over this. And eventually we have to decide on, we have to determine experimentally what, if any, the brain uses. Next couple of lectures, I'll talk about learning in the brain, but it's very local. There's another thing that's about this algorithm is you have to propagate information all the way forward and save all that information for when you compute the for when you go backwards, right? This basically, this H goes in here. This is computed on the forward pass. Okay, so there are lots of reasons the backprop doesn't work very well. And I may say a few words about biology of plausible alternatives, but it's kind of technical. People come up with these just kind of by guessing. There's no real obvious way to go about figuring out what's biologically possible. But it's a huge, very important question in neuroscience. Okay, we have 6 minutes. I think so. I'm going to pause and see if there are any questions. If not, I'm going to sort of really give you just a preview of what we're going to start on the next lecture. And that's something called, well, actually, I'll actually just write down what we're going to do. So remember, we have y is equal to f of w comma x, where f is a deep network. Okay. And we can write this as approximately equal to f of w naught comma x plus delta w dot the partial of f of w naught x with respect to w naught. Okay. So we could truncate our Taylor expansion at first order and use that to train. So this is, so if we truncate at first order, so we're in the neural tangent kernel. It's called the neural. What happened? Regime. So neural tangent kernel, also often known as NTK. Okay. And that's nice because loss is convex. The squared loss is convex. So y minus f of w comma x. Remember, we're minimizing this function. Okay. This is equal to 1/2 the sum on mu of y mu star minus f of w naught x mu minus delta w dot partial of f of w naught x mu with respect to w naught squared. So this is linear regression. Okay. If we're in the NTK regime, we can do linear regression. And we're going to focus on that for probably the half of next lecture, maybe a little bit less, because it gives a lot of insight into at least what these networks are doing. And it's also, when I justify under what circumstances we can actually make the Taylor expansion, it's a good chance it applies in the brain. Really what you need, this is justified if you have a lot of weights. Okay, partially justified. Okay. So it wouldn't make much sense to start that now. So I think I'll end here 1 minute early. As usual, I'll stay on for about 5 minutes if you have any questions. I'll save this to photos before I forget. Okay, so I'll be here for about 5 minutes if you have any questions. Otherwise, I'll see you on Thursday.
dear professor, since
yeah.
the student has no question, I think we can turn the class off. Yeah,
Okay.
the class is over. Yeah.
Okay. Thank
Bye.
you. Bye.
You're welcome.